Thank you, Sujit, for the introduction. This morning's presentation, I'd like to keep this very informal. So if you have any questions, you don't have to wait until the end. You see something on the slides. Please don't hesitate to ask questions. So some of my collaborators are listed. Dr. Panikar and Sarpoder are my former PhD students, and Dr. Srinivasan and Professor Srinivasan from IIT Madras spent some time in Chicago with us. All right, so here's the outline for today's talk. And so there are 4 subtopics. First, I will provide a little introduction to what I consider to be resonant acoustics. And then how do you control these resonant acoustic situations? Most of the time when resonant acoustics occurs, these are not beneficial situations. This is something that can cause damage. So a little bit about high control authority actuators that are used to suppress this resonant coupling. And then we begin with using linear theory first to understand some aspects of flow control. I'm not traditionally someone who has been deep in nonlinear theory, but however, most of the resonant acoustics phenomena is very rich in nonlinear physics. And then finally, we'll use some nonlinear spectral analysis to study mode jumps. For those of you who are interested in any further detail, many of these have appeared in several JFM and Physics of Fluids and Journal of Sound and Vibration papers. Okay, so what are some examples of resonant acoustics? I know there's a combustion community here also, so there are a number of these examples like cavity flows. That's a situation where there's resonant acoustics. Shock-containing jets are resonant acoustics, impinging jets, multiple jet interactions, the Hartmann resonator, and so forth. These are all examples of resonant acoustics. So here is one example is the flow over cavity. And so there are cavities in many applications that can produce intense acoustics, even within pipe flows where they're not desirable. Other application is for aircraft that you have the wheel wells where the landing gear actually goes in. And so those wheel wells have to open. That can produce a lot of noise for the aircraft on the civil side. On the military side, these are also weapons bays where the weapons are actually inside the cavity. So what happens is in the cavity flow, if there's a resonance, you have a low pressure region at the upstream end and a higher pressure region at the downstream end. So anything that's stored in the bay because of the low pressure upstream will have a pitch up moment. Okay, so if something comes out of the bay with a pitch up, you know what happens in aerodynamics? It becomes a lifting body, so it goes back into the bay. Right, so there's been a lot of effort to look at flow from cavities for a number of reasons. All right, now, again, as Sujit said in the introduction, I spent the first 14 years of my career at NASA. So you will see a distinct applied flavor to this talk, even though many of the fundamental aspects have been published in archival journals. So what are some of the problems with nozzles of modern aircraft? And first of all, these are now designed for very high thrust. Okay, so like the F-119 engine, so there are very large dynamic pressures in the internozzle region. The second thing is that modern aircraft, they have significantly advanced materials, so they've got special coatings on the outside, okay, and layered coatings. And in the old days, if the acoustics were very intense, then that caused structural fatigue. It's called sonic fatigue failure of aircraft components, and the metal parts actually had to fail and fall off the airplane. But in modern aircraft, even if the paint peels or the layer peels, then that airplane can then become visible on radar, right? So the standards are much higher. Now, complex nozzles. If you've looked at the nozzles of older airplanes, usually circular nozzles, single twin, F-16 single, F-15's twin. If you look at more recent airplanes, all of them have beveled edges, presumably for lower radar cross-section, so they have beveled edges. So, so what happens is the nozzles are non-uniform. So in addition to being non-uniform, the nozzles are also variable area ratio and variable aspect ratio. So circular nozzles, you could have like an iris opening, closing, variable area ratio. Here they are variable area ratio, variable aspect ratio. It's two-dimensional, rectangular or square. All right, so you have a very complex system of actuators and things like that that control these. And last point is called human factors. So if you have an airplane on the deck of an aircraft carrier, and you have people very close to it, they're exposed to very high levels, and hearing protection is not really sufficient. You know, they actually wear these things on the back. It's called kidney guards to make sure that the vibrations, you know, actually don't hurt the human body. So these are some of the new issues. So here's a picture of the F-15 Eagle. This is an Air Force Research Lab photograph. So you can see here, so the flaps that you see, those are the afterburner flaps for opening and closing the afterburner. But on the outside, there are supposed to be aerodynamic flaps to provide a smooth flow over the exhaust, over the nozzle, right? But in this case, those have been removed. That's because there was intense acoustics in coupling between the two jets, and that caused sonic fatigue, and that made those external nozzle flaps fail and fall off the airplane unpredictably in flight. So they preferred to actually remove the external nozzle flaps. Even though there's a 2% aerodynamic penalty, it's better to have a 2% aerodynamic penalty, you know, with certainty rather than unpredictable change. Okay, so here is a picture of one of the early versions of the F-22. Again, you can see now these are double beveled, you know, complex geometry nozzles. And there could have been damage in certain cases. Okay, so again, we're just covering some basic fundamental physics first. So in supersonic jet noise, there are multiple components. Okay, so the first component, this is called jet noise. The one, jet mixing noise. Most of what is considered jet noise by the commercial aircraft community, some of that is jet mixing noise. There's also broadband noise. So you can see this noise is radiating at 30 degrees to the jet axis. The flow is coming here in this direction, and the noise is radiating at 30 degrees. This is called broadband shock noise that radiates both forward and aft. Okay? And in the spectrum, this is the jet mixing noise, this is broadband shock noise, and then of course you have tonal noise in some cases, and this is the near field of tonal noise. Now, broadband shock noise also gained a lot of importance. If you, many of my aircraft examples are US-based aircraft, like the Boeing 777. Apparently, at some point, they had some issues with broadband shock noise. And at cruise, of course, it's a turbofan engine, so the primary is running subsonic, and the secondary is actually choked. So there's broadband shock noise. And they're very concerned about broadband shock noise also because the jet mixing noise mainly radiates in the aft region, right? Whereas broadband shock noise goes both forward and aft. And in any airplane noise situation, those of you who are in aeroacoustics, you know that you never want the noise from the engines to go forward, you know. And what's the reason for that? Because who sits forward? These are the people in first class, right? So you don't want them to have any noise. The noise going aft is more or less tolerated a lot better. Okay. So so this is the screech phenomenon. Again, so I'm trying to give you the background and coming to resonant acoustics. So in resonant acoustics, you have 4 processes. You've got a growing instability wave in the flow. Then you have a shock vortex interaction, vortices interacting the shock, and then the production of upstream feedback, and then finally you have a process known as receptivity, with the acoustic wave couples with the hydrodynamic wave, and then you have a self-sustaining resonant loop that can produce very intense acoustics. So And the processes are shown here. So you have the instability wave growth, instability shock interaction, acoustic feedback, and the receptivity process. So you can have instability waves, of course, for small perturbations. Those are linear growth. But then when the amplitudes go up, they are nonlinear. And the shock cell models and unsteady shock motions can be modeled. And source location and details of propagation in the near field have been studied also. And then finally, you have this effect of scattering by the nozzle lip and coupling of acoustics and the hydrodynamic waves. Okay, so again, those were the 4 steps: the instability wave growth, the shock vortex interaction, the acoustic feedback, and the receptivity. And this is true in most resonant acoustic situations. You will find that this will, if you look at the cavity flow, it's a similar thing. There's a shear layer growth, there's impingement on the downstream edge, and then there's feedback, and then there's the coupling, similarly with the impinging jet. So you have fairly similar physics. Okay, so now the relative dominance of which one of these is the most important, has not been very clear. So Alan Powell actually is the one who first discovered screech in Southampton in 1952, and he advocated at that time itself viewing the resonant screech loop as a limit cycle, and there are 4 factors: instability wave growth, shock instability wave interaction, feedback efficiency, and stream disturbance creation. So he called it stream disturbance creation in those days, in the 1950s, but later on that term receptivity is used for that. Okay, now there's been a lot of work in this particular area. I'm just using screech as an example of resonant acoustics. And so a lot of the early work was work done in Southampton in England, and then followed by some work in the Netherlands and also in Canada. And then there seemed to be a gap, and then there was a lot of work done at NASA Langley, and then our group at NASA Glenn did some work on that. The middle block went ignored for many years. There was a big chunk of work done in the former Soviet Union, which became known to people in the West much later. And then there are some examples there of where you may think some of their advances that they made were quite significant. So, okay, so let's talk about unresolved issues with this. Okay, so this is a very fertile ground for all kinds of investigations. So in this resonant acoustics, whether it be screech or cavity tones or anything, you have mode jumps. Okay, so you can have a frequency mode that all of a sudden jumps to another mode. You can also have spatial modes, like for example, axisymmetric mode jumping to azimuthal modes, or you can have, in 2-dimensional cases, you will have spanwise modes. So in a circular jet, you have axisymmetric mode, helical mode, first helical, second helical, then combination of first helical in both directions, plus minus 1, plus minus 2. Similarly, in 2-dimensional geometry, what happens is if the aspect ratio is very large, then it's mainly the flapping mode. If the aspect ratio and in the other direction is uniform, the aspect ratio is small, you can have flapping mode. You can also have spanwise symmetric and anti-symmetric modes. So you can have modes in both directions. Now, so the first part, that's the first thing. The mode jumps are unpredictable, and so far, to the best of my knowledge, I don't know of a method to be able to predict these mode jumps. When the mode jump will occur, most people can predict kinematically permissible frequencies, but the dynamics of it, are very complex. The second one is that instability waves are modulated by shocks. Often we consider, linear stability and or exponential growth of disturbances, small disturbances growing, but when you have shocks in the flow, the picture is a little bit different. First of all, in a jet, it's like having a shock train, right? Compression, expansion, so there's flow convergence, divergence, and so forth. So you don't see that classical exponential growth, and the shocks, instability waves can be modulated by the shocks. Okay, then linear theory can predict both shock spacings approximately and frequencies. Frequencies are based on the length scale set by the shock spacing, but it cannot predict amplitude, of course. And the complex geometry nozzles that I showed, such as the ones on modern aircraft, any recent airplane has non-uniform edges, they're beveled edges, or they have the flow exhausting on an adjacent surface, like the B2, because that's like a thermal shield. So you don't have the flow just exhausting to the ambient, it exhausts on a short surface. Okay, so, and then these multiple jets can couple in various modes. Then the last point I have is the reflective surface in the near field has a very profound effect on the acoustics. All right, so let's talk about each of these points from here. So these are the unresolved issues, and I'd like to give you something to think about many of these points, and these are also possibilities for future investigations. So the mode jumps are unpredictable. So in a circular jet, there are various axisymmetric modes possible at different frequencies, and then there are helical modes, and then there are flapping modes, and so forth. And there are distinct jumps in frequency and mode shapes, and there's been a lot of work in this area, but still there's no clear answer for when these mode jumps will occur and why exactly they occur. Okay, so here's the second part. This is the instability wave growth that's modulated by the shock. So it's a normalized disturbance amplitude on the y-axis versus a downstream distance. Then you see these arrow locations. This is where the shocks are located. This is the first shock cell, second, and so forth. Okay, and so at those locations, it appears that the instability wave is modulated by the shocks. There have been several explanations for this, and I will try to, without going too much into this, so. First, there was photographic evidence that showed that the vortices, they accelerated, decelerated, and so forth. And it was clear that, so this type of exponential growth that you see in linear theory is not to be expected when there are shocks present. And there are many reasons. And without reading through this, so let me just tell you. So again, the shock train, compression, expansion, it's like having a channel with convergent, diverging, that changes the instability wave characteristics. Second, you have the shocks present, so there are whatever vortex is actually jolted every time it goes through the shock, right? So you see that. Then there's a third explanation, and that is that you have these downstream propagating hydrodynamic waves, and then you have upstream propagating acoustic waves, and that may be setting up a standing wave pattern. Okay, and then you have this intense standing wave in the near field, and so when you try to measure these things, you might actually see these dips, and you may actually be measuring the very near hydrodynamic field of those disturbances. Okay, so those are the possible explanations. Yes.
The previous slide, that was a modulation of amplitude, not of growth rate, right?
Yeah, so this is the log of the normalized disturbance amplitude on the y-axis. Okay, so it's like a u prime normalized by an initial u prime, and versus.
You're modulating growth, but you're modulating actually
right.
The strength of the disturbance.
That's right. Okay, so. All right, so I gave you those explanations, and then the second part. Let's talk about the shock very quickly about the shock cell spacing. So one thing is remarkable to note that despite the fact that this phenomenon is a highly nonlinear, you can model many aspects using linear theory. The shock cell spacings and the frequencies are modeled, and so in rectangular supersonic jets, those were linearly perturbed in Tam's model, and then in his case, the shock cell system in the jet column was bounded by a mixing layer, and that was approximated by a vortex sheet. These are the initial ideas of Prandtl, and there was a model by Prandtl, and then later Prandtl-Pack model. And that problem was solved by an eigenfunction expansion. And then the solution to the eigenvalue problem yielded explicit shock cell spacings. Okay? And then Morris also worked on this, Phil Morris, and And the difference between Tam's and Morris's work is that Morris used a boundary element method for accommodating nozzles of arbitrary cross-section instead of the eigenfunction expansion. And by both methods, the vortex sheet provides decent estimates of the shock cell spacing. Okay? So I find this to be an interesting result because a linearly perturbed supersonic jet is not the same as a shock-containing supersonic jet, yet the linearly perturbed supersonic jet gives you the shock cell spacings that you would expect in a real situation. Okay? All right, so this Prandtl pack model has been known for some time, and there have been further things done like a multiple scale shock cell model, and this is all, again, all linearly perturbed supersonic jets. Okay, and so I'll show you, here's a comparison of experiment with the linear model. So the shock cell spacing, S over H on the y-axis versus fully expanded Mach number on the x-axis. And so the models appear to predict or reasonably they're validated by experiment. And the figure on the bottom is non-dimensional frequency versus fully expanded Mach number. And those are experimental data points from various researchers. And then depending on the phase velocity that you choose, in one case the phase velocity is 0.55, in the other case it's 0.7, you can match that data. Okay, so here then I said one of the other unresolved issues was the presence of reflective surfaces. So here's an example. This is a under-expanded jet at Mach 1.7, and the top figure in the Schlieren image, there's a very thin lip nozzle, and of course here we thickened it excessively, but you don't have to thicken it that much. But so you can see that a very large, intense acoustic phenomenon occurs. The screech intensifies. So you can say, well, by putting a surface at the lip, right, there's like a pressure doubling effect, right? So then even for tonal acoustics, the level should only go up like 6 dB. But in this case, the levels go up like almost 20 dB. So it's like, very unpredictable effect of reflective surfaces. This is another lesson to be learned from this. If you're ever working in flow control of a jet, people often employ actuators to control the jet. So to mount the actuators, sometimes they install a flange near the nozzle, and then they put the actuators on the flange. So you have to remember, by putting the flange, you're making the situation far worse than it actually is in terms of the acoustics, and then you're using the actuation to reduce the noise. But if you didn't have the flange, you wouldn't have this problem to start with. So again, there are many, and some of you who are exposed to the aero side, you know that whether it's for aircraft engines, the installation effects are very important, right? So you can see the effect of reflective surfaces. All right, and then here is an example of the complex span-wise shock cell structure. So remember I showed you those modern aircraft, and so they have essentially beveled nozzles. You can either have it, so it's like taking a nozzle and then you have an oblique cut. Okay, so then what happens in this case? Okay, this is uniform two-dimensional nozzle or rectangular nozzle. So the shock cells are more or less uniform. And in this case, at a certain Mach number, there's some asymmetry. Okay, and then when it's beveled like this, you will have essentially span-wise oblique shocks. So the span-wise modes will become oblique. So in addition to your transverse mode, that's a flapping mode, you have a span-wise mode, that's oblique mode. And then you have this double beveled nozzle. And so you can see those are the shock cell shapes. And depending on the Mach number, you can either have this behavior, which is antisymmetric, which means half of the jet and the other half are out of phase. And in this case, at a certain Mach number, they are uniform. It's like span-wise uniform. So again, there are these significant complexities. And now when you bring two rectangular jets close to each other, they can be coupled and synchronized in a symmetric mode, or they can be coupled in anti-symmetric mode. One is going like this, other is going like that. Okay. So again, they produce very intense acoustics, and in many cases it was found the coupled symmetric mode produced higher levels in the internostril region, and then the coupled antisymmetric, it produced lower levels. Okay, so this first part was about the basics of resonant acoustics and what are some of the unresolved issues in resonant acoustics. Now our eventual goal is first to understand resonant acoustics, but then it's also to suppress this resonant acoustics. So how do you suppress resonant acoustics? Okay, so you saw in that there are multiple things, that instability wave growing, some interaction, feedback, and so forth. So you can, essentially you need to destroy the feedback loop. You can do it in many places. You can somehow maybe condition the shear layer so that it doesn't support disturbances, the growth of disturbances. That's one possibility. You can maybe also tailor the downstream edge so that the impingement doesn't occur in a certain manner. Or, and in some cases, they also destroy the span-wise coherence in the initial shear layer. Okay, so exactly what happens is sometimes hard to discern only because everything seems to be connected. So, all right, so that's our goal, to suppress resonant acoustics. So one needs to use certain actuators for suppressing resonant acoustics. Okay, so if you look at the literature and if you look to see what industry is doing, you will find that there are two classes of actuators. One class is that type of actuator that's used in most university laboratories. These can produce very interesting results for fundamental studies, but however, they don't really have the control authority to be used in a practical application. Okay, so you have to have sufficient control authority for the higher speeds. Also, the actuator needs to be much more robust. I'll talk to you more about that. So our focus has been on more practical actuators. So even actuators we study in the lab are ones that could be used in flight, you know. And some of this is perhaps due to those 14 years I spent at NASA, because I had a boss who always said that if it will not fly on an airplane, then I don't want you to do it. So, all right, so for this flow control system, many of the things we have done are open loop, but then you need to have some knowledge of the flow phenomena, and then you need to select the actuators and sensors and the control algorithm. So with this actuator, what we're hoping to do is you want to inject perturbations at a prescribed frequency, amplitude, and phase into the flow where the flow is most likely to be receptive to it, so that you're expending minimal energy, right? And you're using the appropriate frequency. So we saw some examples yesterday about loudspeakers and certain other types of actuators that can produce very interesting situations in the lab. But when you go to a full-scale aircraft application, you need to have something that's very robust. So in this slide, I call this 11 habits of effective actuators. So this is like a laundry list of what you would like to have in an actuator. Okay, so it should be controllable in frequency, amplitude, and phase, right? You like it to be high bandwidth, which means if you have an actuator that can produce 500 hertz, the same actuator can produce 10 kilohertz. Not always possible, okay? You want it to have a high dynamic range, preferably no moving parts, okay, because the robustness, reliability is compromised if you have moving parts. Low power requirements, fast response, ease of integration, and ease of miniaturization, that you can actually, for example, you want to build these actuators into the body of the nozzle. You cannot have in a flight application things sticking out. And you'd like it to be insensitive to temperature, insensitive to electromagnetic interference, and especially when it gets to aircraft applications, and finally low cost. It would be very hard to meet all of these criteria. So, but you have to pick something that would do a decent job and proceed. So, all right, so what we found is that if you can somehow leverage a resonance mechanism, that's good for the actuator. So you have, let's say, piezo electric element on material on some structural member, and then you use the second bending moment of that structure, or you use devices that have high, that exhibit aeroacoustic resonance, okay? So let me give you one specific example. Now, most of you who have worked with any acoustic type actuators, and see my focus has always been noise reduction, right? So noise reduction, you find if you use an actuator for it to have high control authority, the actuator itself makes noise, some noise, like a loudspeaker or a resonance tube that makes noise. So while you're reducing the noise of the jet, you're injecting actuator noise, so your net noise benefit is diminished. So if you can find an actuator that makes less noise, then you're likely to have a better net noise benefit. Okay, so one thought was, what if you made the actuator ultrasonic? So all of the aircraft noise metrics are based on PNL, which is based on human perception to sound. So anything above 20 kilohertz, really doesn't count. So you can make as much noise as you want that's not audible to the human ear, and in the PNL metrics, which is called perceived noise level, those things don't count. Okay, so if you had an actuator at 1 kilohertz, that's the worst frequency to have the actuator at, because it's going to add significant perceived noise. Whereas if you had an actuator at 25 kilohertz, it may function fine and it doesn't add any noise. Okay, so we set out to develop a flow control and noise reduction actuator that's inaudible to the human ear, and so the actuation frequency is greater than 20 kilohertz, but it should also be capable of high amplitude. And you can do this using flow resonant actuators or resonant actuators that need mass flow, and it can be robust with no moving parts. Okay. All right. So we looked at this Hartman resonator. We've seen some of work that Hartman did, where you have a flow that's aimed at a tube. The tube has one end open and the other end is closed. Okay, and so what happens in that? So it's based on aeroacoustic principles. So during one phase, the oncoming flow will compress the air in the tube. That's the compression phase. And then that compressed air will kick out, which is called the evacuation phase. So there's an alternate compression evacuation phase. So you have very high pressure perturbations in this region, with no moving parts. Okay, you can get wide range of frequencies. That's if you put a piston, because this is based essentially on the quarter wavelength type behavior of the tube. Of course, to be accurate, it's a quarter wavelength, but you also have to have appropriate end corrections for very, very shallow tubes. Okay, so if you had a piston here and you change this, you can also get different frequencies. So it's a fairly robust actuator, and in this case, you can actually see the oncoming flow and the resonance tube. Let's see. Is it working there? Oh, anyway, so this pressure front here, you will see that oscillating. Okay, it's that you can that's okay. We'll proceed with this. It's okay you can visualize that. Okay, so this is our construction of the miniature powered resonance tube, which is an ultrasonic powered resonance tube. So you can see that we are able to produce 25 kilohertz here in this 135 dB, fairly intense acoustics. And this is just shown at some conditions, 60 psi. It's not necessarily optimized. And so again, this is built into this. There's an adjustment needed to get the correct spacing between the supply jet and the resonance tube. Okay. So this case, let's look at this. This is a very interesting case. So this is from the Hartman resonator type situation, and this can function at the whole range of frequencies, from fairly low frequencies to high frequencies, all the way to 25 kilohertz. And I want to point out one feature, and let's see if this. Okay, it's working here. So these are different frequencies, 3, 5, and 9 kilohertz. Okay, so while this is playing, you can see that it's the same actuator functioning at different frequencies. In one case, the dominant hydrodynamic perturbations are being directed in a certain direction. In another case, it's going both upstream and downstream. And in another case, it appears to be so in this case, you can see it's dominantly propagating in this direction, right? So in this case, it's propagating both this direction and this direction. Okay, so just a word of caution here. Often when you use a fluidic actuator that produces tones, you have to be careful when you attribute effects to and call them frequency effects. So if you use this actuator at different frequencies and you will produce different results, and you say, well, these are frequency effects, but these are not really frequency effects. These are the fluidic actuator is behaving differently at various frequencies. Okay, so one needs to distinguish. So it's not the same thing as having a loudspeaker and dialing through various frequencies. You start low frequency, high frequency, and then you can plot the behavior versus frequency and say these are frequency effects. But in this case, the actuator characteristics themselves are significantly different with frequency. Okay, so we go back now to this ultrasonic actuator. I'm going to show you the results of the ultrasonic actuator. And here we'll use jet impingement tone horizontal ground plane. So the jet impingement tone is really the jets are aimed at a ground plane. So in our facility, so in a normal real life situation, you have a vertical takeoff and landing aircraft. The jets are aimed at the ground and the airplane lifts off. In our facility, what we do is the jets are fixed and we move the ground plane down. Okay, so the horizontal ground plane is for vertical takeoff. In some cases, we also done an inclined plane, which is like what's called as the blast deflector on the aircraft carrier deck. So, so in this case, this is again what I've told you earlier you should be careful about doing. We have changed this design. So if you put a flange around the nozzle, you're going to intensify the acoustics, okay? And then you can use these actuators to reduce it, so you need to be careful about that. So I won't describe the setup here, but you can see a circular nozzle, and those green with the red, those are the miniature ultrasonic actuators. And the red part is used to change the spacing between the supply jet and the resonance tube, and you can see the resonator tube itself in red, and then the traversing mechanism is in green. Sorry. Okay, so let's look at this, and this is something we found repeatedly in many phenomena. Okay, so all the red curve on the right is the baseline case that there are significant tonal acoustics, and then the green is with suppression. Okay, the ultrasonic actuator is turned on, so you can actually see here the 25 kilohertz peak. Okay, so this is something interesting we found, that in most cases where there are a lot of low frequencies, if you introduce a very high frequency tone or high frequency actuation, it appears to wipe out all the low frequencies. So the putting in the 25 kilohertz essentially dropped all those tones, all of the tonal acoustics at low frequency is gone, and you have only the high frequency, but you don't care about the 25 kilohertz only because in jet noise metrics, the perceived noise level will take out that it's not audible to the human ear. Okay, so on this left-hand side, you see OASPL is overall sound pressure level suppression. Then PNLT is perceived noise level, which then PNLT is a tone-corrected perceived noise level. And so what is tone-corrected perceived noise level? So perceived noise level is, if you take whatever noise you measure with the microphone, that's your basic noise measurement. But then if you apply weights that correspond to the sensitivity of the human ear, those are perceived noise level. And then tone correction, what that means is that there's a penalty added for the presence of the tone. Okay, so which means that 90 dB broadband doesn't sound as bad as 90 dB with the tone, so you add a penalty for the presence of the tone, so that's the tone corrected noise level. And then the tonal suppression is just how much you drop the tone. So the tone, we drop the tone by almost like 30 dB. So that's just a tonal suppression. Okay, so, all right, so let me tell you what the problem is now. So you have a nice actuator that can take care of impingement tone suppression in the vertical takeoff and landing situation. So if you talk to a nozzle designer in an engine company, or somebody in the aircraft industry, they would say that this mass flow that we need for the powered resonance tube, which is 1% of the main jet flow, there's no way you can do that, because that would need a compressor bleed. And if you speak to anyone in the engine industry, GE or Pratt, 1%, first of all, compressor bleed is, they won't talk to you once you use the word compressor bleed. You know, and bleeding 1%, you know, is generally not, and most of the newer engines, they try to be bleedless, like so. Okay, so that is still an issue. So it's still a nice lab experiment, but bleeding compressor. So you only have two choices. You either carry air on board in compressed gas tanks, or you bleed the compressor, right? Okay, so. So how do we implement this in a practical situation where you're not allowed to bleed the compressor, but you'd like to introduce this high frequency actuation? And so the actuators that use compressed air, okay, they need compressor bleed or bottled compressed gas. So we'd like to use the same type of method without air. Okay, so we sought a way to do this, and during this time, Air Force Research Labs, this is the Wright-Patterson Air Force Base in Dayton, they had been developing methods for cavity acoustic suppression, and they also had difficulty finding suitable actuators, and they had some results and they couldn't explain, so we had a program with them. So this McGrath, Shaw, and Stanek strategy was to use a very slender cylinder upstream. And the shedding from the cylinder is relatively at high frequency compared to the cavity frequencies, okay? So a similar approach. So you don't have the high frequency Hartmann actuator, but you have high frequency cylinder that is tailored so that the shedding from the cylinder would be at a high frequency. Okay, so the shedding from the cylinder is at much higher frequencies than the Rossiter modes. And this was used first in this McGrath and Shaw study, and by Leonard Shaw later for controlling cavity resonance. They called it high frequency tone generator. It's so HFTG, but that's just a cylinder. Okay. So I was involved in some experiments at DARA in the UK, looking at the effect of the cylinder, and we found that there were some optimal locations. The cylinder dimensions had to be about 2/3 of the boundary layer thickness, and the height of the cylinder from the floor, which is the upstream part of the cavity, had to be 2/3 also of delta. But remember again, there's a lot of literature on shedding of a cylinder, right? But remember, this is slightly different. This is shedding of a cylinder in the proximity of a surface. And once the flow goes supersonic, first of all, you've got parts of the cylinder that are seeing different flows because you have the cylinder immersed in the boundary layer, right? And then you will have, in the supersonic cases, the shocks in some part of the cylinder. So it's a little bit more complex situation, but it's illustrated here that you have your boundary layer delta, and then the cylinder is somewhere here. Okay. All right. So our first try at this, we compared the Hartmann resonator, which is a powered resonance tube bank. This is in this picture, to the rod. And the rod is in this picture. Here's the powered resonance tube. Okay, so this is the Stanek paper in which I was also involved. And so you have the white curve is the baseline, and then you have the blue curve with the Hartman tube with significant mass flow, and then the red curve is the rod and cross flow. Okay, so the rod did reasonably well. In some cases, it does better without using any airflow, and you can drop the tonal acoustics by about 20 dB. Okay, so here's the next question. So how does this rod work? What exactly is it doing? Okay, so there are multiple hypotheses at this stage, right? So one thinking, or one line of thinking, is that the wake of this cylinder alters the stability of the shear layer. Okay, so it's like having a shear layer profile and having a wake profile superimposed on it, and if that's now stable, then you don't have disturbances growing. That's one possible hypothesis. The other hypothesis is this high frequency forcing hypothesis that was initially advanced by Ari Glaser at Georgia Tech. And his hypothesis, which is not proven in this case, but is that when you put in very high frequencies, it's like adding, dissipation, and so that dampens all the low frequencies. Okay, that was his. Okay, but in a cavity, you have to be careful, because when you put something upstream, you can just simply lift off the shear layer. So many of these hypotheses you have may not really be in effect. You just lift the shear layer off so it doesn't impinge on the downstream edge. So that's also a possibility, right? So this is the shear layer liftoff shown in a calculation where here the rod, this is the baseline case, and then the rod is immersed here, and then that shows the rod actually lifts off the shear layer. So again, you'll find in some cases the rod can lift off the shear layer. In some cases there is no lift off, but again there's acoustic suppression. So we're trying to understand this. Why is this happening? So one approach was to, okay, fine, let's see what we can do with linear theory. And what we'll try to do is look at the amplification envelope and see where the Rossiter modes are and what this rod does to it. Okay, so we had an experiment where you could have, here's a rod upstream of the cavity, and the rod could be moved to various heights, various distances. This is the rod. There's a coolite that measures the rod shedding characteristics. There's a microphone in the cavity. There's a hypodermic probe, and there are various locations possible. Okay, so we could do a study. Okay, so even before doing the experiment, you can do a very quick check, and that is you can create these what's called synthetic velocity profiles, and then look at the stability of these synthetic velocity profiles to simulate the rod, and I'll explain that in a moment. So if you look at, if you actually measure the velocity profile with the rod present, you're going to see a shear layer profile plus a wake profile superimposed, right? So you can build a profile like this, and I call it synthetic profile because you created this shape that has the shear layer characteristics, which is a tan hyperbolic profile, and then superimposed on that is a wake profile, and then you adjust all these things. B is the shear layer momentum thickness, C is the wake deficit, E is the width of the wake. You can change them systematically to see what's happening, right? And then, so we started with this part. Okay, so, and then what's plotted here is minus alpha I theta versus frequency, which is the amplification of the linear disturbances versus frequency, the amplification envelope. Okay, so you can see here that for the baseline profile, which means there's no rod, this is just the baseline profile, the growth rate is very sensitive to the momentum thickness of the shear layer, right? So the growth rate is sensitive to the momentum thickness of the shear layer. That's not a surprise. We expect something like that. And then let's look at the effect of C, which is the velocity deficit of the wake. Okay, so this, if you can change the velocity deficit of the wake. Now you find that there are two modes. Okay, there are two eigenfunctions, 1 and 2. Mode 1, and then you can see here that mode 2 is more unstable than mode 1, and mode 2 is insensitive to the velocity deficit of the wake. This is the velocity deficit of the wake. The scales are different on these axes, so this mode is more unstable, and it's insensitive here. It is sensitive to the deficit of the wake, but it's not a highly amplified mode. Here it's an amplified mode, and it's insensitive to the deficit of the wake. Okay, now we look at the z-axis shift, which is the effect of A plus D in this synthetic profile. So you look at A plus D. Okay, that effect is we look at here. So mode 2 here again is insensitive to shift in velocity profile. All right, and then you look at the wake profile, the effect of D, and so this mode 2 is also insensitive to the shift in the wake part of the profile, but unless it overlaps with the tan hyperbolic part of the shear layer profile. And then this is finally the width of the wake. So you change the width of the wakes, and this is all done with no measurements. So just a synthetic profile. You just look at this. Is before we do the experiment, you'd like to make sure that before you expend significant time and effort, that you do some quick analysis to see if it makes sense what you're trying to do. So with mode 2, again, you find it's insensitive to the width of the wake. So these were the results based on the synthetic velocity profiles, which means this is for a compressible mixing layer plus wake profile, there's more than one unstable mode. So you have a mixing layer profile plus wake, you have two unstable modes. Mode 1 is sensitive to changes in the wake part of the profile, and mode 2 is sensitive to changes in the mixing layer part of the profile. Okay, and then when the wake and the mixing layer they start overlapping, that's when the cylinder is very close to the ground. Okay, that influences both mode 1 and 2. So bringing the wake closer to the mixing layer increases the growth of mode 1 and reduces the growth of mode 2. All right, so this said, okay, fine, now let's do the real experiment. So let's measure the velocity profiles and then fit those, and use real measured velocity profiles for the stability analysis. Okay, so now I'm going to bring in one other case. So you have the baseline, which is just the flow of the cavity. This is our cavity block, and so flow will be going like this. So this is the baseline. Here's the rod, which I call it shedding plus wake, okay, which means the cylinder will have a wake plus it's shedding in an organized manner. In this case, we put the cylinder actually on the ground, which is called non-shedding plus no wake. And in this case, you wrap a wire, helical wire, to spoil the cylinder. Okay, you wrap the wire around the cylinder so that you still have the wake of the cylinder, but there's no organized shedding. So actually, we had done a number of studies to examine various wire thickness and the various pitch of the winding. And we found actually that if you just go to the parking lot and measure the car antenna, what the pitch is and what that thickness is approximately, that's the correct answer. So we don't have to do all these parametric studies. Somebody's already done it for us. But we found it in retrospect after going through this exercise of different thicknesses of wire and different pitch windings. So now you can see what I'm trying to do. We have rod that's going to have a rod that's shedding and one that's not shedding. Okay, so because those who were critics of this approach said that maybe it's just putting the rod, the wake of the rod is what's doing it. It's not the organized shedding, right? So, okay, so this is our facility, and then so we'll go to the experimental results directly. So here we have three cases. You have the rod, you have a baseline case which with the high tones, which is just the cavity, and then you have what did I do? So you have the baseline case, just the cavity, then you have the rod, which is what I call shedding plus wake. And then the rod with the wire wrapped around it is called non-shedding plus wake. So there's a wake, but there's not shedding in organized manner. So the shedding plus wake shows this organized shedding, right? So it clearly destroys all the low frequencies, but then you have this high frequency. You don't care. Again, this is 40 kilohertz. So it's not an audible noise. But this is not a jet noise application. But okay, so this is at Mach 0.6 and this is at Mach 0.7. The reason we did multiple Mach numbers, we always want to make sure that you don't have just a point solution that only works at one Mach number and doesn't work in other conditions. So you want to do a range of Mach numbers. Okay, so you can go a little bit closer to see only up to 20 kilohertz. You can see baseline, non-shedding plus wake. So both of these appear to, both of them, whether you have the rod with shedding or the rod with the wire wrapped around it is not shedding, both of them drop all the low frequencies. You can't see the high frequency because I cut it off at 20 kilohertz. You go back to the 100 kilohertz, you see this, okay, at both Mach numbers. So the baseline had high resonant acoustics and the shedding frequency is clearly visible. And shedding frequency is an order of magnitude higher than the frequencies you're trying to suppress. Okay, and this is again at Mach 0.7, the same thing. The intense acoustics is destroyed by this method. Okay, so this business of the stabilization of the shear layer, let me explain what we're trying to do here, and using this. Okay, so in this case, what we're solving is the compressible Rayleigh equation. And if you look at this amplification envelope, if you calculate this envelope for the measured velocity profiles, and if your Rossiter frequencies are within this envelope, that means they are still amplified, okay? Now, with the rod and cross flow, there are two possibilities. Either with the rod and cross flow, the Rossiter frequencies are still within this amplification envelope, in which case you did not change the stability characteristics of the shear layer, or for some reason, if they're outside, you can say that now you have modified the shear layer so that those disturbances that are no longer amplified, right? So that's what we're trying to show. And so to do that, now we did it with all of these cases where the velocity profiles were actually measured, and you can already see that all of these Rossiter modes are well within the amplification envelopes. So for each case, you put the rod in, you measure the velocity profile, you do the stability calculation, then you put the rod with the winding on it, you measure the velocity profile, you do the calculation, but you find that these Rossiter modes, R1, R2, all of these are within the amplification envelope. Okay, and these are our measured velocity profiles. And you can see that, so really what we're doing is we are creating a composite velocity profile that models both the shear layer portion and the wake portion, and then using that for the stability calculation. All right, and so the results were the same as we saw before with the synthetic profiles. Another thing we checked that to make sure the velocity profile is not just.
I'm trying to make the connection with the talk of Ulrich Haschereit yesterday. Group in here Berlin did something similar. They said, okay, let's measure average velocity profiles for different levels of different amplitude of fluctuation. And then we said the limit cycle amplitude should be the one where the linear stability gives you marginal stability from the average velocity profiles. Now you're with synthetic profiles are doing something similar, but I don't quite understand how amplitude figures in your equation, because these are always experiments where you measure the profiles in limit cycle of resonant amplitude, right? You have no way of...
Yeah, no, in this case, we don't have the resonant amplitude. This is just the shear layer portion, isolated. We're only looking at the shear layer, you know.
But the measurements where, say, sound pressure level is changing, this always corresponds to a limit cycle.
That is correct. In the analysis, that is correct. In the measurement, you know, that corresponds to the limit cycle.
And then if I naively apply the thinking of T. Berlin, I should expect that I should always see marginal stability also for your analysis. Or where did I do wrong?
I'm not that familiar with the Berlin. I heard Oliver's presentation yesterday. So in this case, what we're doing is the experimental part is real life. So you're measuring, you have a resonant acoustic situation where you make the measurements. In the linear analysis is completely idealized. You're not looking at anything resonant there. You're just looking at the shear layer and saying that what would happen if you had, instead of a tan hyperbolic profile, a tan hyperbolic with a wake profile. And seeing what is the tendency of that to go unstable, under what conditions. So that's the...
That gives the almost like the apart is positive, you're going to have noise. So it's not about finding the amplitudes, right?
Yeah, and this is just saying that we're trying to out of the three possible hypotheses, see which one is more likely. Okay, so and then we measured the profiles at various locations in the span-wise direction. I'll come back to you on this. And so you can see the span-wise coherence of the high-frequency shedding. So the rod is actually shedding uniformly in all directions. We have more detailed measurements in the near field through phase average measurements that showed the shedding from the rod under various conditions and the noise that it was radiating to the near field. Okay, so what did we learn from this part, which is the rod and cross flow? So we're trying to understand how the rod and cross flow is suppressing cavity resonance. I don't think we have all the answers. And we did this using a combination of acoustic data and stability analysis. And so as per the linear stability theory, frequencies corresponding to the Rossiter tones were always unstable, okay, no matter where the rod is positioned. And so in other words, one of the hypotheses was that perhaps the rod is stabilizing the shear layer. So disturbances no longer grow, and that's the reason that it's suppressing. That doesn't appear to be the case. So it could be one of the other hypotheses, either the hypothesis that putting in very high frequencies, that is also, in my opinion, not very likely. So it could either be the lift-off theory, or in some cases, perhaps the high-frequency effect is doing it. Okay, so in the last part, I want to talk a little bit about using nonlinear spectral analysis to study twin jet coupling. And one of my PhD students was involved in this, and also a visiting faculty member from IIT Madras, Professor Srinivasan, was involved in this. So we go back to the twin jet problem. Okay, so the twin jet problem again is you have two jets in close proximity to each other, and certain modes they are coupled and symmetrically, certain other an anti-symmetric mode, and the phenomenon is fairly unpredictable, and there are these mode jumps. Okay, so and we will be looking at two-dimensional geometries that are beveled so that you have these span-wise modes. So you can have a single beveled exit, and I think I have this is a nice picture of that. Okay, so we have two microphones on either side of the span of this single beveled nozzle. Okay, so the single jet modes are the two solid squares showing that those two are in phase. That's a symmetric mode. And solid square and unfilled square showing that this is out of phase, which is the anti-symmetric mode. And then these two boxes, this shows that it's like an oblique mode. There's a phase variation is an oblique mode. So if you have a two-dimensional geometry with an oblique exit, those are the three possible span-wise modes: span-wise symmetric, span-wise antisymmetric, or span-wise oblique. Okay, if you have the two nozzles pointing like this towards each other, the bevels, you can either have them bevel this way, or you can have them pointing towards each other. In this case, the jets are actually directed away from each other, right? So it's inhibiting coupling, so they don't couple in the case at the bottom here. There's no coupling. In the case, so we call it like arrowhead, and then there's the V-shaped. In the V-shape, you can again have either the two fill circles, which is a span-wise symmetric coupling mode, or you can have a span-wise antisymmetric coupling mode. You can have, those are the coupling modes possible. Okay, all right. So you can see here that in this case, they didn't couple. In this case, they are coupled in a symmetric mode at low Mach numbers, and then there's this mode jump, and then all of a sudden it's coupled in an antisymmetric mode at the high Mach numbers. Okay. Why this jump occurs is it's not very clear. So you can see from the figure at the bottom that these are the two, the circle and these two in black are the original jets. Each jet individually, the sound pressure level from each of the jets versus Mach number. But then in the couple case, you have the red curve. So the levels are significantly higher when you have the symmetric mode. When you have the antisymmetric mode, the levels are actually lower. So that's a beneficial type of coupling. All right, so in this experiment, one of the things we did is you could change, you have two nozzles side by side, you could change the nozzle spacing, you can change the Mach number, and you can also change the supply pressure, which is like an engine pressure ratio. Okay, and so initially, we also checked for phase coherence. These jets are phase locked, so they are both going like this or they're going like that in a phase locked manner. And you can check the coherence between them. All right, now in this case, we analyzed the time series further and looked at the microphone power of one relative to the other at various Mach numbers. And before we go to the higher order spectral analysis, you can just look at time series of acoustic pressure from one channel plotted against other in terms of XY phase plots. And there's some hints of nonlinearity from the fuzziness and curvature when you look at these phase plots. Okay, so then we're going to do what's called time localization studies. So you can have various phase plots plotted, with X phase plots, different windows. And so these are cross spectra for XX, YY, and XY phase plots. And the XX and YY plots are dissimilar, but the XY plots look similar. Okay, so one of the things, what we are trying to do is we're used to working with linear spectral analysis for the most part. You look at the spectrum. But then by going to higher order spectral analysis, you can learn a lot more. And so the linear spectral analysis, also in this case called second order spectra, that cannot discern between linearly superposed and quadratically modulated signals. Okay, so we go to higher order spectral methods. So there is a cross bispectrum. Some of this started, in the electrical engineering departments many years ago at the University of Texas at Austin, and then subsequently they were used. Higher order spectral analysis was used by by Thomas and Chu and others at the University of Notre Dame to look at shear layer modes. Okay, so we use the cross bispectrum, so this quantifies the relationship between a pair of frequencies in the spectrum, and you can also look at the cross bicoherence. Okay, so all right, so this has been used before, like we were not the first by many people have used it. So higher order spectral analysis in shear flows, Thomas and Chu used it in 91 and 93. They looked at planar shear layers and traced the axial evolution of modes. Then Walker and Thomas looked at a screeching rectangular jet and looked at axial evolution of nonlinear interactions. And Thomas also has a book chapter on higher order spectral analysis applicable to shear flows. So you can see here in this demonstration that if you create two sinusoids, sine omega 1t plus sine omega 2t, f of t and then g of t, you multiply both of them, you look at the spectra, and you look at the cross bicoherence. So let me just tell you our motivation for using this twofold. One is in many of these resonant acoustic cases, there are multiple modes, right? And then once you have a few of them, you can have sum and difference interactions. And it's difficult to say from the final spectrum, how, let's say you have multiple modes, whether you don't know whether F1 plus F2 gave you F3 or was it F3 minus F2 that gave you F1, so the sum and difference interactions. The other motivation for using nonlinear spectral analysis is that we'll show that in some cases it can give you some clues on these mode jumps, when these mode jumps are going to occur. All right, so here is a figure that shows the interpretation of the cross bicoherence results. So in this plot, this is the spectrum you will get from conventional linear spectral analysis. Okay. Now the green line shows the participating frequencies, 1 and 2, and then 3 shows the resultant frequency. Okay. So it can tell you which are the two frequencies that combine to give you the third frequency, the resultant frequency. In this figure, this is the sum interaction region, and this is the difference interaction region. Okay, so in this case, the influence of phase on the cross bicoherence, we introduce in this the g of t equals sine omega 1t times sine omega 2t plus epsilon. And so you can find that for various phase, the cross bicoherence is insensitive to small phase differences, but then it declines very sharply if the phase difference is much larger. Okay, and then this is the effect of magnitude on the nonlinear part. And so here the nonlinear part is systematically varied. So you have a times f of t plus b sine omega 1t times sine omega 2t plus epsilon. And you can see the resultant spectra of g of t and cross bicoherence between f and g. The cross spectrum looks similar, only the magnitudes differ. Okay, so even with, let's say, with a and b 0.5, you can detect the nonlinearity. If you have a small amount of nonlinearity, you can still detect it. Even with a 0.99, b 0.01, you can detect it. So you can detect with higher order spectral analysis even very small magnitudes of nonlinearity. Okay. All right. So here we'll use second order and third order spectra for the entire parameter space, and then look at changes in gross features in higher order spectra. Okay. And see if we can use this to look at nonlinearity. Okay, so here we go back to those two jets, the V-shaped and the arrowhead. So in the V-shape, you know that there was coupling, and in the arrowhead case, there was no coupling, right? So in the case that didn't couple, you're not seeing anything in this nonlinear spectrum. In the case that coupled, you're seeing some stuff we'll look at in more detail. For single jets show lower nonlinearity than twin jets in basically in terms of the number and strength of the interactions. So the dots, you can count the dots, so those are the number of interactions, and you have the color bar for the strength of the interactions. Now this is in the symmetric coupling range, you have these interaction clusters at, you can see it at 2 different Mach numbers, you have these interaction clusters. And as the Mach number increases, the mode switches, and you go from these clusters to some kind of a lineal pattern. It's like it lines up along a straight line. And so here's the clustering. So it's really, these are just combinations, f plus delta f, f1 plus 2 delta f, and f1 minus delta f, and so forth. These are small. Okay, this is close-up view of a structure. And as the nozzle spacing increased, the number of nonlinear interactions increased. Okay, so this is the effect of the nozzle spacing. And this is a closer look at the lineal pattern. All right, so now what we're going to do is we're going to count the number of nonlinear interactions and call it interaction density, which is number of peaks in the cross bicoherent spectrum above a certain threshold. So you can set a threshold value and count the peaks above the threshold value. So this interaction density can then be looked at. So you can actually see the interaction density with a threshold of 0.3 versus the fully expanded Mach number for various cases. And you can see the single jet values are the lowest. And then as you go to multiple jets, the cases that coupled strongly have higher magnitudes. This is shown with a different threshold at 0.4. And this is the average interaction density versus Mach number for in this case, it's shown average interaction density for various spacings. So this is something I want to point to now. What is the value of this? What we're finding is, so remember this unpredictable mode jumps that occurred? So we are finding here that the number of nonlinear interactions, if you count the number of nonlinear interactions, they seem to start increasing before the mode jump. Okay? So the increase in the number of nonlinear interactions appears to be a precursor to the mode jump. So before the mode jump occurs, you see the nonlinear interactions actually increasing, and so the mode jumps are shown on the top, and the interaction density, which is the number of nonlinear interactions, is shown in the bottom. This might provide some interesting possibilities. So let's say you are in an engine situation where there's likely to be some mode change that is detrimental or damaging. You have a metric now that's a precursor to the mode jump, and before the mode jump occurs, you see something that starts changing. So we have consistently found those mode jumps. Okay, so we said, okay, let's do this. When there's a mode jump, you see the number of nonlinear interactions beginning to increase. So now let's look at a case where there is no mode jump. What happens to the number of nonlinear interactions? So in case where there's no mode jump, there is no increase in the number of, so here's a case with the 2 jets aimed at each other, and this is a single jet where there's no mode jump. So this is the phase difference between these 2 microphones, phase difference almost 0. That's a uniform symmetric mode, no mode jump, number of nonlinear interactions also stays quite flat. If you have 2 jets directed at each other, again with no strong coupling and no mode jumps, here they are coupled actually antisymmetrically, but no mode jump. It's 180 degrees, and you can see the number of nonlinear interactions stays flat. Whereas the cases that had the mode jump, you actually saw the nonlinear interactions beginning to increase before the mode jump. So we thought this is an interesting observation, that if you can count the number of nonlinear interactions from the cross bicoherence and track them, they give you a signal that there's going to be a mode jump. Okay, so what did we learn from nonlinear spectral analysis? One is that, so there is this metric that's been used a lot in electrical engineering previously. It's been used in fluid mechanics also, but you can use that higher order spectral analysis to look at these nonlinear interactions. And configurations that did not show conclusive linear coupling were found to be nonlinearly coupled. So nonlinear coupling may be important in nozzle design. And the nonlinearity can be graded. So there were patterns of cross bicoherence, one that was clustering, another that had alignment. And then there's also a new interaction density metric. So you can use this to quantify nonlinear coupling. And this average interaction density appears to peak in the vicinity of the mode jumps, and it starts rising before the mode jump. Okay, so this is our hope that nonlinear spectral analysis may be a useful tool to look at these interactions and mode jumps. I mean, there are clearly a number of unresolved issues. But this is something, you know, which could become part of your toolbox, just as you use linear spectral analysis, you know, using nonlinear spectral analysis on these signals, you know. So let me end here. Thank you very much for your attention.